Every story has a beginning, but this one requires us to go back to the first possible second. To understand how we got here, we have to account for what happened during that initial flash, why the process began, and where all of existence actually fit. That starting point occurred roughly 13.787 billion years ago. While we often think of the Big Bang as a finished event from the ancient past, it describes a process of expansion and evolution that is still driving the universe forward today. The event is difficult to visualize because space did not exist before it. The Big Bang created and stretched the very fabric of space as it moved. Think of the universe as the two-dimensional surface of a balloon. That surface represents all of space, while the air inside is pure, intense heat. As the balloon inflates, the surface area grows from a microscopic point into a massive sphere. Every atom of matter that would ever exist was packed into an unimaginably small space on that surface. Within fractions of a second, that space stretched across astronomical distances. We are currently living on the surface of that balloon, riding the wave of an expansion that has been stretching the distance between galaxies for billions of years. The growth began with a phase called cosmic inflation. In a billionth of a blink, a universe smaller than a single subatomic particle expanded to hold everything we see today. Trillions of degrees of heat meant the standard rules of physics could not function. A theoretical quantum field took over, and in less than 10 to the negative 32 seconds, the universe expanded in size by a factor of 2 to the 80th power. While this specific phase remains a theoretical model, it provides the most accurate mathematical explanation for the universe's current shape and temperature. By the 3-minute mark, the universe cooled enough for the physical laws we recognize to take hold. A single, unified energy split into the 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Subatomic particles filled the void, resulting in a chaotic collision between matter and antimatter. These opposites destroyed one another, leaving behind immense radiation and a small surplus of matter, the material that would eventually form us. During a phase called nucleosynthesis, the temperature dropped to 1 billion Kelvin. This allowed protons and neutrons to finally stick together, forming the first atomic nuclei of hydrogen and helium. In just 20 minutes, the universe moved from a state of pure, chaotic energy to possessing the stable atomic building blocks needed to build every star and planet in existence. After that initial sprint, the universe entered the photon epoch, a period characterized by a much slower, steady cooling. Compared to human history, this era was vast, lasting 380,000 years. On the scale of the universe's total age, however, it represents only the first few hours of a long life. During this time, the heat was still intense enough to keep electrons stripped away from atoms. These free-floating electrons acted like a thick barrier, bouncing light particles, or photons, around in every direction and creating an impenetrable fog. Recombination occurred roughly 380,000 years after the start. As the temperature fell to 3,000 Kelvin, electrons finally settled into orbits around nuclei, forming neutral, stable atoms. As the electrons locked into place, the fog cleared. Light could finally travel across the void, creating a signature we still detect today as cosmic microwave background radiation. This radiation is the oldest light in the universe, a faint glow of microwave energy that fills every corner of space. This cooling turned a blinding, opaque soup of particles into the vast transparent vacuum we see through our telescopes. The clearing of the fog led to the Dark Ages. Because space was transparent but expanding rapidly, the existing light thinned out. The universe became a freezing, lightless void for nearly 300 million years. Even in total darkness, gravity was pulling massive clouds of hydrogen and helium gas together, creating increasingly dense pockets of matter. When these pockets became dense and hot enough, nuclear fusion ignited. These were the first stars, massive nuclear furnaces hundreds of times larger and millions of times brighter than our sun. These first stars ended the era of darkness, flooding the universe with light and beginning the long process of galaxy formation. We can trace the mechanics of this growth with high precision, yet we still look for the context. We have developed several models to explain whether our universe is a singular event or part of a larger system. The multiverse hypothesis suggests our universe is one of many existing simultaneously. In this model, different bubble universes might operate under entirely different physical laws, with some resembling our own and others being completely unrecognizable. Alternatively, the cyclic universe model suggests there is only one universe that exists in a repeating loop. This theory proposes that the expansion we see today will eventually reverse. The universe will contract, collapsing back into a hot, dense point that provides the spark for the next Big Bang. Whether our universe is a single chapter in an infinite cycle or a lone bubble in a vast multiverse, the path from that first microscopic spark to the galaxies of today follows a traceable physical history.